So in this video, I'd like you to try to calculate this integral with pen and paper, and then when you come back to the video, I will provide a detailed solution. But have a go first and enjoy it. Okay, welcome back. Let's look at the solution on the next slide. So here I've written out again the integral that we want to calculate, and the key observation is to realise that actually we've got two integrals here. We've got the sum of two terms in the numerator, and we can break this up into two separate integrals with the x in the numerator and plus with a 1 in the numerator. It's always worth looking quickly to make sure that this sum is not the derivative of the argument of the brackets, but it isn't. The derivative of the argument of the brackets would be minus 10x. So we have two integrals. So we split them up and we look at them. And we recognize that here the numerator is proportional to the derivative of the argument here. So we could calculate this using a substitution, but I personally think it's much easier for a simple integral like this just to write the answer down, perform it by inspection. The second integral I'm going to calculate on the next slide. So we look at this and we think up to a number, which we can always sort out. This is the derivative of the argument here. So if we can perform it by inspection, essentially what we do is we're going to add 1 to the power here. Now this means 4 minus 5x squared to the power of minus 3 halves because it's in the denominator. If you add 1 to that power, you have 4 minus 5x squared to the minus 1 half, and that means 4 minus 5x squared to the half in the denominator. So now, if we differentiate this, and you can see I've left some space here and here, if we differentiate this, do we obtain this? So we have 4 minus 5x squared to the power of minus a half because it's in the denominator. We differentiate it, we pull out a factor of minus a half. We then would reduce the power by 1, and that would give 4 minus 5x squared to the minus 3 halves. And that's great, that's what we want. And then, from the chain rule, we would multiply by the derivative of the argument here, and that would be 0 minus 2 5s are 10, so minus 10x. So we can see that we're going to get this structure here that we want when we differentiate this. We are going to get a factor of minus a half and a minus 10. Minus minus is plus, so that's good because there's a plus sign here. And 10 times a half is 5, and then we have an x. So what we would get would be 5x divided by 4 minus 5x squared to the 3 halves. So this tells us that we need to put in a factor of 1 over 5 here, and I'll just put a 1 there. And now, if we differentiate this, we obtain the integrand, so therefore we have performed this integral successfully. On the next slide, I'm going to perform this integral. So here is our second integral, and you notice that we've got these two numbers here, something positive minus something times x squared, and really a large part of the point of this video is to give you practice in performing a sign substitution, but when there are a couple of numbers other than 1 inside the bracket. So I suggest drawing a triangle, and if our change of variables is going to be any use whatsoever, it must be the case that the square root of 4 minus 5x squared is one of the sides. We're going to make a sign substitution, so that tells us that we're going to have x times some number here perhaps. I'll just put the x down, and this side is going to be the square root of 4 minus 5x squared. So if I square that and I square this, I will get 4 minus 5x squared, and here I will get x squared. They are not going to cancel to something simple. But if I put here in front a square root of 5, now when I square this and square this, the sum is 4. So this tells us that the hypotenuse of this triangle is 2. And we just check, yes, that does satisfy Pythagoras' theorem. So we see, just from looking at the triangle, that the sine of theta is the opposite over the hypotenuse is root 5x over 2. And we can rearrange that. X is 2 sine theta divided by the square root of 5. And we're going to need the derivative dx d theta, so we just differentiate this and we have 2 over root 5 times the cosine of theta. The formula that we're going to use for this change of variables is written here. So we have our integrand, we rewrite it in terms of our new variable, and we multiply by hand by a factor of dx d theta, which we've already calculated. So, and then we integrate with respect to theta. So let's do that. Our integral is equal to, so it's the integral of 1 over, this is the square root cubed. Now the square root divided by 2 is the cosine of theta. So we see from the triangle that the square root of 4 minus 5x squared divided by 2 is cos theta, so it is 2 cos theta. So that is the factor in our integrand expressed very simply in terms of our new variable theta. So here we have the square root cubed, so this is 1 over 2 cos theta all cubed. We now multiply by dx d theta. Dx d theta we've written down here already. So we see that here we have a 2 in the numerator, here we have 2 cubed. They're going to partly cancel, and it will give us 1 over 2 squared, 1 over 4. There is a 1 over root 5 factor there, and I've just pulled all the numbers outside of the integral, and we have the integral of 1 over cos squared theta, because it's cos theta over cos theta cubed. So we have 1 over cos squared theta with respect to theta. 1 over cos squared theta is sec squared theta. Just left the numbers there. And we know that the integral of sec squared theta is tan theta because the derivative of tangent is sec squared. Now, you could work out what the tangent is in terms of sine over cosine, but it's very easy just to look back at the triangle. Tangent is the opposite over the adjacent, so the tangent is root 5x over the square root. So I've just written this again, root 5x over the square root. And we see immediately that the square root of 5 cancels, top and bottom here, making life look rather easier. And that is our result for the second integral. The previous slide, we calculated this integral here. So putting them together, this integral plus this integral, we see that we have, well, this factor is in the bottom of both of them. Here there is a 1 over 5. Here there is a 1 over 4. So a common factor is 20. Here, if we're going to write 1 over 20, we have to multiply top and bottom by 4. And here, if we want to replace that by 20, we multiply top and bottom by 5. So we get the x multiplied by 5. And that is our result for the integral. And on the next slide, I'm going to differentiate it or set that for you as an exercise and give you the solution. So the real point of this video was to give you some practice in looking at integrals where the integrand involves various numbers other than 1, and I do recommend using a triangle. With that, let's look at the next slide. So here is our result for the integral, the one that we just obtained on the previous slide. And I think it's very good practice to verify things like this by differentiating our result. And if you do that, you should use, in my opinion, not the quotient rule, but the product and chain rules. I think it's much more efficient. And on the next slide, I'm actually just going to give you the answer written out, but do try it before you look at it. So have a go at this, and then you can see the answer on the next slide. Okay, on the next slide, I'll show you the answer. So here I'm differentiating our result for the integral to show that it yields the integrand. And the way I would do it is I would pull the 1 over 20 outside. It's just a factor that multiplies everything. I would say that the integrand is 4 plus 5x in brackets, all of it multiplying 4 minus 5x squared to the power of minus a half. And then you differentiate this and multiply it by that, which I've done here. And then you add this times the derivative of that, which pulls down a minus sign. You have to use the chain rule. And then you look at this, put them on a common denominator of the highest power. And then when you do that, you will find that everything reduces. And in the end, you obtain the original integrand. So if you wish, you can pause and check that you've got it right. One comment perhaps is here I extracted, going from here to here, the common factor of 5 everywhere to cancel that down to a quarter. You could have left the 5s in there and seen at the end you get 20 over 20. It doesn't make much difference either way. Okay, with that I'll stop.